Hello everyone. Long time no see, I suppose. I did not expect that last topic to extend so much. But hopefully you like giving a try proving statements. So yeah, I think from now on that's a given, you know. I think I will be proving a lot of things, but anytime I prove anything, feel free to give it your own shot. See if you can prove it on your own. Just pause the video, and if you want to compare answers, maybe then see the rest of the video. Okay, so let's do something easy this time, right? Um, a lot of people tend to struggle with fractions, and I gotta be honest. I think I didn't like fractions myself, maybe until I was like in eighth grade or something. You know, so I mean, I'm there with you. Fractions aren't that easy. However, once you get the hang of it, I think they're actually nicer than you would expect. And in the future, you'll see that actually fractions are much better than decimals. But yeah, let's try not to be afraid of fractions anymore, right? So there's only two things really to know about fractions: how to add them and how to multiply them, right? I mean, like I said, subtracting is just adding negative numbers, adding additive inverses, and dividing. Well, dividing is just multiplying by the multiplicative inverse, right? So as long as you know how to add fractions and how to multiply fractions, I think we'll be fine. I mean, look, it can't be any worse than what I already made you guys go through, right? And I made you guys go through to those videos because it's the only way to prove things, to really, really prove things. So, I mean, yeah, if we didn't have the axioms, right? You'll see that these proofs that we're gonna do today are way, way simpler than me trying to give you a physical representation of why these rules are so. I mean, I can if you wanted me to. I can draw. Oh, this is what division means, so on and so forth. But I think the axiom route is way easier. So I don't know. Like I said, if you made it this far, I think you'll appreciate it. And of course, if you want to have your cake and eat it, if you want to know the axiom explanation as well as like a physical geometry type of explanation, yeah, just let me know. I'll be happy to do it. Okay, so let's once and for all conquer fractions and not be afraid of them anymore. Alright, so fractions, right? Okay, well, alright, before we have to argue about semantics again, let me just define something real quick, right? So, definition. So, the binary operation known as subtraction is really just equal to adding the additive inverse of b, right? Again, so I'm making a definition meaning that this phenomenon is just whenever this phenomenon happens, it's just equivalent to this phenomenon. This one, which is nice in the axioms of real numbers, right? And again, why, right? I mean, well, the fact that I'm defining it means that for my channel, I'm agreeing that this is the way that we look at subtraction, right? But again, if you're not satisfied, let me just do a quick recap. If you let x be a minus b, right? And then you agree that addition should undo subtraction, that means that when you add b to both sides, then you have that x plus b equals a. But then add the additive inverse to both sides, plus additive inverse to both sides. And then we're going to ultimately end up with x equals a plus negative b, right? So again, x equals a minus b, and then it ends up being that x equals a plus negative b. So it's not too crazy to define it this way, right? Okay, why am I defining subtraction? Because now I'm going to define division. So definition. So A divided by B, I'm just going to define this to be so in similar fashion with the axioms, A times B inverse, which in parentheses equal to A times 1 over B, right? And why would that be so? Well, again, the explanation is the same. If you let x be A divided by B, right? Again, same idea. If addition and subtraction undo each other, multiplication and division undo each other, right? So I'm saying multiply by B, both sides, times B, or whatever you want to define multiplication, right? So then x times B equals A, right? But then now multiply by B inverse on both sides, then we're going to have that x equals A times B inverse, right? So again, the act of dividing by B, it's the same thing as multiplying by the multiplicative inverse, right? Well, okay, so let's just put everything together, right? These are all equal. These are all equal, right? What am I saying is equal? So again, right? I already kind of saying defining that A divided by B is A times B inverse, right? So those two are definitely equal. But moreover, I mean, again, I can also write B inverse as just 1 over B, right? And then the last thing I want to say that is equal to all these other ones is just this, which A over B, right? So again, right, I mean, in particular, I'm saying that, I mean, hopefully no one disagrees with me, right? That these two are equivalent, right? That A divided by B is the same thing as A over B, right? And if you can accept that, then you have to accept that A over B is equivalent to all the other ones as well, because A divided by B is equivalent to all the other ones, right? So, if I write A over B, I can also substitute that for A divided by B, which I'll never do because I really dislike this symbol. But I might substitute A over B by A times B inverse, or A times 1 over B. Okay, well, I'm defining what a fraction is, right? Now when you learn fractions, right, for the first time, well, the first thing they teach you is that when you have a fraction A over B, right, the top part is called the numerator, and the bottom part is called the denominator. And you probably hear that once, and then it goes out the window, right? You kind of don't really remember it after that. But actually, remembering the names of each one is kind of the key to understanding fractions. This is just telling you that every time you have a fraction, the top number only just basically kind of tells you how many you have, but it's the bottom number that tells you what kind of fraction you have. So for example, right, like 3/7, right? This just means that if you look at the quantity 1 over 7, you have 3 of them, right? If 3 over 7 just means that if you look at the quantity 1/7, then you have 3 of those, right? Which is funny because, again, right, if you look at all the equal things, right, it kind of matches up if I just wrote 3 parentheses 1 over 7, right? This kind of also means that for whatever quantity 1/7 is equal to, you have 3 of them, right? So again, the numerator tells you how much you have of a certain kind, whereas the denominator tells you what kind. And the reason why this is important is because, for example, if I had 3/7 and then you had to add 2/7, right? what would you think the answer is? Well, I mean, if everything makes sense, you would think you have 5 sevens, right? Because you're saying I have 3 of this type, and I'm adding 2 of the same type. So you have 3 of this type and plus 2 of the same type. I should have 5 total of the same type, right? Which is, again, I can also do this as if there's math going on in the background, right? You have a 3. If 3 over 7, you can write it as 3 1 over 7. And then if you write this as 2 1 over 7, then again the axioms cannot take over, meaning, you know, the last axiom of real numbers, which is the distributive law, which also turns out to be the factoring law, right? I have 1 7 here, 1 7 here, meaning that if I factor 1 7, I would get a 3 plus a 2, and 3 plus 2 is 5, and 5 times 1 7 is just 5 sevens, right? So again, right, just double checking that what I'm saying makes sense, right? If I have 3 of 1 sevens and I have another 2 1 sevens, I should have 5 1 sevens, right? So adding fractions is easy, but only if you have the same denominators, right? Addition of fractions is easy, but only if you have the same denominators. Okay. Right? If you have instead, so 1/3 plus 1/5, right? What is that equal to, right? So now it's different, because now you're saying, you know, 1/3 is one type of thing, 1/5 is a different type of thing. It's almost like asking what's pi plus e. Well, usually with pi plus e, just leave it as pi plus e. However, the good thing about fractions is that actually we will be able to combine these two into one quantity. Okay. But okay, so adding fractions might not be easy if the denominators are different, right? Okay. But one thing that is easy about fractions is multiplying. So hopefully, if you don't remember anything else, you remember that multiplying fractions is the easy one. Okay. Well, how do you multiply fractions? Statement. If you have a fraction a over b, and you multiply it times another fraction c over d, then the resulting number you get is going to be a times c divided by b times d, right? So as you can see, if you've seen my previous videos, I'm about to prove this statement with the axioms of real numbers, right? Well, again, I'm gonna go back into, that's why I said at the beginning, right? Let's look at what a over b is equivalent to. A over b is equivalent to a lot of things, right? But for me to use the axioms, I'm gonna do that a over b times c over d equals a times 1 over b, and then times c times 1 over d, right? So I'm just rewriting this fraction right here, and I'm rewriting this fraction right here, right? And then the thing about multiplication is that multiplying numbers is pretty easy. Actually, that's the good thing about multiplication. You get to shuffle it around. So for example, if I shuffle these two around, then I get that a times c times 1 over b times 1 over d. Okay. Now, let me put it right here on the side, just as a food for thought, right? The only way I'm going to prove, so a over c times divided by b over d, so this part is equivalent to ac divided by bd, right? Okay, maybe it's also equivalent to AC times BD inverse. Okay, one more time. It's equivalent to AC times 1 over BD. Now it's looking like I'm almost done, right? The two fractions I started with is equal to A times C times 1 over B times 1 over D. And I want to, if I can just get that it's equal to A times C times 1 over BD, I will be done. Well, am I done? I would say maybe not quite, because I don't know the following. Is 1 over b times 1 over d equal to 1 over bd, right? If it is, then I'm done, basically. But what if it's not? So then in the middle of this proof, we're gonna prove something. Statement 1 over b times 1 over d equals, without a doubt, 1 over bd. So I mean, again, 1/3 times 1/5 equals 1/15, right? So that's an example. 1/3 times 1/5 will, without a doubt, after we prove this statement, be equal to 1 over 15, right? So how do I prove this statement? Well, proof. So how do I prove this statement? Well, here's the one thing that I'm going to prove. 1 over BD equals BD inverse. Meaning, 1 over BD is the multiplicative inverse of BD. So again, if you go back to the axioms, very, very special, multiplicative inverses are unique. So for example, if any number I multiply times BD and I get 1 as a result, then that number that I multiplied has to be the multiplicative inverse. So what am I going to do? I'm going to prove that I want to show that 1 over b times 1 over d is the multiplicative inverse equals BD inverse, right? So how am I gonna do that? Well, just multiply it. 1 over b times 1 over d times, again, if I'm going to claim that this is the multiplicative inverse of BD, I need to multiply this to BD. And hopefully the result is I get a 1. Well, I have 1 over b times 1 over d times b times d. And again, this is why division sucks, right? We wouldn't really have, according to the axioms, we don't have anything about division, but right now I'm multiplying things. I have this times that times that times that. So if I shuffle these two, AB equals BA, then I have 1 over B times B times 1 over D times D. And now it works out. 1 over B times B is going to be 1, and 1 over D times D is going to be 1. 1 times 1 is 1. And I think that's it, right? I showed that when you multiply 1 over b times 1 over b to BD, you will get a 1. So 1 over b times 1 over d is indeed equal to BD inverse, which is indeed equal to 1 over BD. Right, 1 over b times 1 over d equals BD inverse. That's what I just proved. And BD inverse is just another way of writing 1 over BD. I know it's blurry, but again, I proved the statement, right? So then, yeah, if I go back to the original proof, then so going back to the original proof, we said that A over B times C over D equals yada 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 equals A times C times 1 over B times 1 over D. This is where we stop. But then now, because of the thing that I just proved intermediately, then this equals A times C times 1 over BD. And again, so this is equal to A times C over BD. I mean, again, it's a little awkward finishing this, but again, you can go back to a lot of things, right? You can go back to what even is a fraction to see that when I get to this point, then it's equal to AB over CD. Okay, so proven, whatever, right? So now we know that multiplying fractions is just you multiply the top with the top, and you multiply the bottom with the bottom, and it's as easy as that. That's how easy it is to multiply fractions. Well, what can we do? What can we do now? Well, an intended consequence is the following. Note. Notice this one thing that happens, right? If you have a fraction, a over b, it's a real number, right? Well, anything is equal to itself times 1, right? But then the fun thing about 1 is that 1 can be anything, really, right? If I say 1 equals c over c, no matter what the c is, well, as long as c is not 0, because you can't divide by 0. But as long as c is anything that's not 0, right? This will be okay to do, right? I mean, because c over c, let's say, is c divided by c. And can you negate that anything divided by itself is 1? Or again, that c divided by c equals c times c inverse. And this, according to the axioms of real numbers, is indeed 1, right? So the thing is that so a over b equals a over b times 1, but 1 can be equal to c over c for any c that's not 0. And then what did we just prove? That when you multiply two fractions, you multiply the top with the top, so a times c, bottom with the bottom, b times c. So ultimately, right, any fraction a over b is equal to a over c over b over c for anything, right? What am I saying again, right? Well, look at, I mean, I'm saying that, 1/2 equals 1 times 2 over 2 times 2, which would be 2 over 4. Well, let's say that now I multiply by 3. So 2 over 4 is 2 times 3 over 4 times 3, which is now 6 over 12. What I'm saying is that a fraction can look many different ways, but still be the same number, right? Okay. Well, I know how to multiply fractions. I want to know how to add fractions, right? So let's go back to 1/3 plus 1/5, right? I can only add fractions, or so far you accepted me, maybe so far with me, that you can add fractions as long as they have the same denominator. So if only these fractions share the same thing, well, I just told you I can rewrite fractions in all sorts of ways, right? So if I could only find a way to turn both of these fractions into fractions that have the same denominator, what could I do? Well, maybe in 1/3's case, when you multiply it by 1, you multiply it by 5 over 5. And in the 1/5 case, maybe when you multiply by 1, you multiply it by 3 over 3. And thus, now you have that 1/3 equals 5 over 15 plus, and 1/5 equals 3 over 15. And now they have the same denominator. So what's 5/15 plus 3/15? Should be 8/15. So that's what's 1/3, 1 plus 1/5 is equal to. We were able to manage to put two fractions into the same one fraction, right? So then in general, so statement. So you have a fraction a over b, and you try to add it to a fraction c over d. Well, you know what? I mean, I'm saying statement, but let's just do the math right here, right now. What would I do next? in order for the denominators to match, well, here, I just multiply by kind of like the other denominator and it worked. So I would multiply A over B times D over D, right? And then C over D, I would multiply it by B times B over B. So I would end up having AD over BD plus CB over BD. And then now that they have the same denominator, now I can just add them, right? So I would have AD plus CB over BD. Now, I mean, again, I'm not even going to write a proof because this is the whole proof right here, right? But I just want you to know that this is the one situation in which I just wrote a statement where you don't really have to remember the rule. The really rule to remember is that as long as they have the same denominator, you can add them. The case that I'm trying to show you is this, right? An example is if you had 1/2 plus 1/8, right? Now, according to this math that I did, you can multiply this 1/2 by 8 over 8, and then you can multiply this 1/8 by 2 over 2, and that will work. If you do that, and let me do it below. So 1/2 times 8 over 8 plus 1/8 times 2 over 2, right? If we do this math, we'll definitely get the same answer. But what I'm saying is that instead of me telling you this is how you add fractions, right? The really thing to remember is more that you can write any fraction as A over B as something else that fits your logic, right? And then as far as adding fractions, all you have to do is match the denominator. So what I'm saying is that if you only have to match the denominator, well, what I suggest is that in this situation, you don't do anything at all to the 1/8. Because if you have 1 over 2 times 4 over 4, this will guarantee that now the 1/2 has an 8 as a denominator. And then the 1/8 already has an 8 as a denominator. So if you continue this way, you get that 1/2 equals 4 over 8. So 4 over 8 plus 1 over 8, the answer is 5 over 8. So what would have happened if you would have done it the other way, right? If you've done it the other way, again, you will get the same answer, but I feel like you're gonna do a lot more work. So for example, let's do it, right? 1/2 times 8 over 8, you get 8 over 16, again, right? Top times top, bottom times the bottom. And then 1 over 8 times 2 over 2, you get 2 over 16, right? And if you have 8 over 16 plus 2 over 16, you're gonna get 10 over 16. And hey, you might be thinking, oh, wait, I didn't get the right answer. Well, actually, it's going to turn out that these two are equal to each other. So the fact is, your teacher will always want you to give the fraction that's the most reduced. Meaning, 5 over 8, there's no common multiple between 5 and 8, right? Like, there's no number I can pull out and cancel. But in 10 and 16, there is, right? Both 10 and 16 are multiples of 2. They're both even, right? 10 is 5 times 2, and 16 is 8 times 2. And, at this point, if, from years of math, you're going to want to, like, cancel those two, right? But, and that's correct. But I just want to show all my steps, right? 5 times 2 over 8 times 2 is going to be equal to 5 over 8 times 2 over 2. And yeah, 2 over 2 is 1, so 5 over 8 times 1, 5 over 8. So again, honestly, yeah, if you're in a math class, yeah, you can just cancel these two and say, oh, the answer is 5/8. I just want to say, this will be like showing completely, probably more steps than you need to, right? So again, that's what I want you to remember. All you need to do for adding fractions is to have the same denominator. You don't always have to do this thing where you multiply. There might be cases where you have to, but there might be other cases where you don't have to, right? So yes, the math that I showed you here works all the time, but there might be some cases where you recognize, maybe I don't have to do as much math. I can be a little bit lazy. Let's see. Two more things. So of course, I'm gonna go over half an hour. Well, I keep saying that as long as two numbers have the same denominator, you can add them. So let's just actually make that prove that statement. So the statement is that if you have one fraction and then another fraction, but they have the same denominator, then supposedly is x plus y over c, right? This is really the statement that I'm saying. Well, that's the statement that I'm saying, but actually it's gonna be easy to prove. So x over c plus y over c. Again, this is where you have to recall what a fraction even means. So in particular, I'm going to choose to decide that this means x times 1 over c, and that y over z is just y times 1 over z, right? And then now this might seem familiar. What I'm going to do, I'm going to factor. So if I factor 1 over c, I get x plus y. And then what does x plus y times 1 over c mean? Which is equivalent to x plus y times z inverse. Well, I'm just saying, yeah, we're done. This is x plus y over c, right? And again, when I prove this, so that big deal when I say prove this. By the way, when you think of x, y, and c, what do you think? Do you think of natural numbers? Do you think of integers? Do you think of rational numbers? Or do you think of just maybe random real numbers like square root of 2 or pi? Because when I do a proof like this, I'm proving it for all of them. So when you look at me doing a proof, right, you might think, oh, you might picture this is a 3, this is a 5, this is 7. Hey, I'm proving that for if this is pi, this is e, and this is the square root of 2 as well. I just want to be clear on that. And the reason why I bring this up is this other statement that I want you to show you before you leave. Statement. Well, again, we can add fractions, we can multiply fractions. So, I mean, I'll let you figure it out, how do you subtract fractions if you really want to do that. But then, how do you divide fractions, right? So this is very common. So a over b divided by c over d. So people tell you, right, maybe you remember this from high school, that dividing by a fraction is the same thing as multiplying by flipping them. So a over b divided by c over d is equal to a over b times d over c, right? Well, let's prove this statement, right? If it's really a rule, we should be able to prove it, because it definitely wasn't an axiom, so we should be able to prove it, right? Well, how would I prove this? Again, proving it with axioms is that a over b divided by c over d. Well, again, what I just said, remember on the side. What does say I say x divided by y, what does that mean? It means a lot of things, right? It obviously means x over y. That's one thing. But it also means x times y inverse. And then it also means x times 1 over y. So out of all the possibilities that I'm going to choose to handle this division sign, because I have a lot of options, the option I'm going to choose is to prove that is to rewrite this as, so a over b is like my x and c over d is like my y in this case, right? So out of all the 4 options I have, what am I going to choose? I'm gonna go with this. So a over b divided by c over d equals a over b, that's my x, times c over d inverse. And if you haven't caught up by now, right? Every single time I point out, oh, this is the multiplicative inverse of something else. What do you think I'm gonna do? Well, I know that my end result is that I want to prove that this is equal to a over b times d over c. And the a over b is like not important. A over b is not even going to do anything. So if you see a connection, what am I really going to do? I'm going to prove this, right? That d over c is the multiplicative inverse of c over d. So I will show that the multiplicative inverse of C over D is just D over C. Well, I'm talking a big game, right? How am I going to prove that? Well, there's no other way. The only way you can prove that something is the multiplicative inverse of something else is by multiplying it to what you're saying is the multiplicative inverse of. Meaning, I'm going to multiply this times C over D, and hopefully I get a 1, right? Well, C over D times D over C. Well, hey, I'm just multiplying fractions, right? So it's C over D times D over C. Well, how do I know how to multiply fractions. Multiply the top with the top, the bottom with the bottom. So C times D is CD, and D times C is DC. But the good thing is that, again, A times B equals B times A. So D times C is C times D, right? So I have CD divided by CD, and any number divided by itself is 1. So there, right? Thus, D over C is the multiplicative inverse of CD, meaning D over C equals CD inverse. And I think that's it, right? That was a proof. Again, to summarize, if I really need to summarize, is that A over B divided by C over D was A over B times CD inverse, again by the definition I made you agree to in the beginning of the video, and then right now I just shown that C over D inverse is nothing more, nothing less than D over C. And that's what I wanted, right? That A over B divided by C over D equals A over B times DC. I always forget to mention something. I'm sure that I'm forgetting to mention something, but hey, I feel like we learned a lot about fractions. Hopefully. Again, yeah, hopefully you're not afraid of fractions anymore. So multiplying fractions is the easy thing to do, and then adding fractions should not be a scary thing to do anymore. All you need is the denominators to match, and one way you can find make the denominators match is by multiplying by 1, right? To rewriting basically fractions, rewriting a fraction into an equal fraction that just looks different but fits your purpose. All right. Well, I'll leave it there before this video is way bigger than it needs to. Goodbye. Don't forget to like and subscribe. Leave a comment if you have any more questions. And see you next time. Okay, I just can't help myself, right? The reason why I like to prove things with axioms, what I made you suffer through it, instead of just proving things like maybe drawing a picture, is, let's go back to 1/3 times 1/5, right? 1/3 times 1/5, right? Do you remember the answer? Well, let's figure it out. Try to use it like a picture wise, right? Suppose that from here to here, let's say that's 1, right? Now, okay, so if I cut this in 3s, right, we would have this. Now, suppose the same quantity, right? If I was able to, I don't know, cut this in 5 equal parts, then maybe that doesn't look right, but okay, it's not drawn to scale, right? So this would be 1/5, right? And this would be 1/3. Okay, so again, right, I mean, the math is, okay, you can't really add them unless they have the same denominator. Well, suppose now that, so I cut this line by 3, right? Suppose now that I cut it in in 5, each one. Right? So if I do this, then 1/3 would be 1, 2, 3, 4, 5 out of 15, right? Which kind of goes hand in hand with what we know, right? 1/3 equals 5 out of 15. And then, similarly, if this is 1/5, suppose I cut the each one in 3s. So now I cut this one in 3, cut this one in 3. So I should use this. Cut this one in 3, cut this one in 3, and cut this one in 3. Well, then now I'm back at 15s, right? But this time I see that 1/5 is now what? 3 out of 15. So if 1/3 is 5 out of 15 and 1/5 is 3 out of 15, then yeah, 1/3 plus 1/5 is equal to apparently 8 of them, right? 8 of 15. Right? So that's 5 of the 1/3, and maybe you could say these 3 together right here are the 1/5, right? So 5 and then 3 are the 8. Or you could say these 3 are the 1/5, and what was it? I guess up until here, right? Which kind of does match the picture above, surprisingly. But this would be the 1/3, which is also 5/15ths, right? So either way you look at it, the answer to 1/3 plus 1/5 is 8/15ths, right? Okay, so that's all nice and well, right? But then, what if I'm asking, because you never know, I'm asking you what's 1 over pi plus 1 over e, and you try to draw me a picture of that. How do you cut a 1 into pi things, right? So how would I prove to you that what this is, right? According to the axioms, if you remember the axioms, this quantity should be equal to, let me just do really fast math in my mind, pi plus e over pi times e. So if whatever this is the calculator, pi plus e will be the top part of the fraction, and whatever pi times e in the calculator is going to be the bottom part, whatever, right? But yeah, there's kind of really no way to explain this with a picture, I don't think, or maybe I'm just not gifted. So that's what I'm saying. When you use axioms to prove a statement, you're proving it for all real numbers. Like I said, I can make you a video of proving a lot of things geometrically, but yeah, the whole point of creating axioms is to separate the physical world from the, I guess, mental or logic world. So I just wanted to show you why I decided to, with my channel, to go the axiom route instead of the prove it by picture route. Alright, so that was a little bonus.